Today we have the team from TU Delft, Rcrisp. I met them earlier this year for a workshop, and they are developing a tool that's very, very interesting, and I think it could be very, very useful for some of the teams in RCN. So I'll give the floor to Claudiu, Francesco, and Yehan.
Yes, hello. So, hi everyone. Yehan, myself from TU Delft, and Francesco from the Netherlands Science Center are very happy to present you Rcrisp, which is a tool for automated and scalable delineation of urban river spaces. Our presentation is structured in 3 parts. Each one of us is going to present one part. I'm going to start with an introduction of the challenge that we are addressing, and the method and why we developed a method and tool to address that challenge. Yehan is going to continue with a specific use case that we want to share with you, and we will end the presentation with a demonstration of Rcrisp given by Francesco. Okay, so starting with urban river spaces, I don't think I have to explain the importance of urban rivers to this audience, but I will highlight a bit the spatial dimension of that. So that's a very important component of our approach to urban rivers. So we are referring here to urban river spaces. So as you know, until not so long ago, so a few decades ago, rivers or urban rivers had been seen as infrastructures that can or should be tamed, which resulted in citizens and urban life in general moving away from the riverfront. Now, what we see in the last decades is a kind of process of reversal, return to the river. So we see all kinds of projects of river restoration, river renaturalization, daylighting of rivers that have been put underground before that, or simply downgrading streets or removing cars from the embankments to allow pedestrians and cyclists to reclaim those spaces. So there's some sort of a reversal process or some sort of need for a more sustainable urban transformation of those kinds of urban spaces. So what you see in this slide is just a few examples of projects. One is in Munich on top. In the middle, we see Seoul and Singapore, and on the bottom, we see Paris. But there are many more cities around the world where such transformations are happening. Now, as this trend continues, urban river space boundaries are determined without a systematic and reproducible delineation method. So without a systematic way of drawing the boundaries within which a certain phenomena is understood. So delineation is done wherever suitable spatial data is available, based on census tracts, using rivers as boundaries very often, or using neutral square or circular cutouts at different levels of aggregation, city, district, neighborhood, or areas of study specific to a local urban. So what I want to say here is that there are many different ways of drawing boundaries around the river. That is a challenge in itself. So what you see on this slide on the right is the example of Bucharest, where neighborhood boundaries are very often on the edge of the river. So the river itself is a boundary on sub-administrative level. So then the question arises, okay, well, how do we understand the river? Where do we consider it? Is it on the left embankment or the right embankment? Who does the river belong to? There are all kinds of questions that are relevant for across domains of application. And this is a case of the so-called modifiable aerial unit problem. This is a fundamental problem in geography, according to which, depending on how you draw the boundary around the phenomenon, the conclusions that you draw about that phenomenon can be different. And this is especially the challenge when dealing with integrated local spatial analysis. So meaning that there are all kinds of different aspects that need to be considered of environmental, social, infrastructural kind that have their own logic and have their own boundaries. So how do you combine those? That becomes a more and more complex question. So what we found in our research is that an integrated understanding of urban river spaces requires spatial morphological units of analysis that reflect the combined footprints of environmental, social, and ecological processes. So some sort of a neutral boundary of morphological kind that can be used to integrate different layers and across domains of application. What is very important in this approach is that the river is central. It's never a boundary. So this led to the development of a method and tool of morphological delineation, which we consider to be close to neutral, if not neutral. The method uses street network, openly available street network data and digital elevation data. And it carries out the delineation in 4 steps, and it leads to 4 different kinds of boundary or delineation. So starting in the diagram on the right of the slide here from the bottom, the valley is delineated based on a digital elevation model. So basically based on the terrain around the river, the resulting valley edge is used as one of the inputs in the next step. So the valley here is basically the space that has been carved out by the river through time. And it's not the same as the watershed. The watershed is much larger than that. Then in the second step, the urban corridor surrounding the river is delineated on the street network along a path following road center lines that is closest to the valley edge. So this step is basically a translation of the valley in the topography onto the street network. You see that with the red dotted line here in the middle part of the diagram. The delineated corridor is then divided into corridor segments bounded by the main transversal streets, and that's the green dotted line here. So basically identifying the main crossing lines along the corridor and using them as a way to segment the corridor into smaller units. And finally, on top of the diagram, you can see the river space, which is the space between the river and the first line of buildings. So this is the last layer of analysis. And they increase in level of detail. So the valley boundary is used to characterize the topography of the river as a whole, whereas as you move upwards in this diagram, you gain more and more detail in delineation. And each of these different levels, each of these 4 levels of delineation can be used to answer different kinds of analytical questions, depending also on the level of detail desired in that question. So I'll show you a few examples of applications of this method using Rcrisp. Here you see again the city of Bucharest with the river Dâmbovița crossing the center of it. The darkened area is the valley that was delineated in the first step. Using the street network, we delineate the corridor boundary. That's the orange line. And the thinner orange lines are the segment boundaries. So basically the subunits that are obtained by cutting the corridor with the transversal lines. There's another example, Köln in Germany, the valley, the street network, the corridor boundary, which is cut then into smaller units with the transversal lines. And finally, the example of Warsaw with the valley, the corridor drawn on the street network, and its subdivisions with the transversal lines. Delineation can serve multiple different applications, as I mentioned already. So what you see here is two examples which are more of quantitative kind. So on the left, you see a segmentation of the corridor of the same river in Bucharest, and an analysis of public transport coverage on corridor and segment levels. So here you see the corridor level analysis, and here you see a segment level analysis. And on the right, you see another river where green space coverage is analyzed both on corridor and on segment level. Now, these are examples of quantitative analysis, but you can imagine that the same boundaries can be used to identify, to kind of delineate some sort of phenomenon for qualitative analysis as well. Moreover, with such a neutral method of delineation, there is a potential for large-scale cross-case analysis, especially considering the increasing availability of spatial temporal big data, both in terms of vector and raster data, which presents an opportunity to analyze urban river spaces at large. So trying to understand what similarities and differences exist between a large number of river cities. And here I would like to hand over to Yehan to show you a use case of this kind.
Yes, I think you can hear me well. Yes, so following what Claudiu just introduced, I will show you here an example about how it was used on a larger scale. So here we focus on all the rivers in cities in Europe, and that the cities have a population larger than 250K, and it is crossed by a river. So then we found that using Rcrisp, we can delineate into 663. You can see how it is relocated. It is located across Europe. Here, the case of Warsaw, it is also so starting from the valley level and then go to the corridor, and then they're using Rcrisp to have more segments. So here in Warsaw, for example, the river here, it was divided into 7 segments in the city, and we have this across many cities in Europe. And what I was doing next is I want to see what are the morphologies inside those river spaces. We want to generalize into different types. And to do that, there are quite different morphology including the street networks from also the open source data, the building, the blocks, and also the river shape, and also the density of blocks, the river surface, the river crossings, how it is crossed by the bridges and tunnels, and also the segments that is calculated regarding the area parameter, something like that. So these are all the morphologies that is surrounding and including inside the river. And we also calculated the semiosity of the rivers. So then it was found that in total, those 600 more segments was clustered into 5 different types. And you can see this is how so far it's how it is distributed. And then there are quite a lot of variables that we calculated, and there are some of them they have the same function, and they are quite collinear. So that's why we removed some of the variables, and you can see here the right table is how it is left for our analysis. And here is how the 5 different types of clusters. This is quite maybe abstract to see, but in general, they are based on the variables that we can find for each type. There are some highest and lowest values in different variables. And here we can see it in more in a clear way. So the first one, you can see these are the 5 most representative types in the cluster. And for the first one, for most of the variables, it's not much extreme features. But for the second type, you can find the size of the segment, it's small, and it has more straight river across it. And for the second one, the river is more curly, meandering, and also it has a large sanctuary area of the inside this segment. The fourth one is more open, affected by the traffic. There's less traffic across it. And for the last one, so the size of the segment is large, and it's more densely built, and also has more traffic networks inside the segment. So the way that use case is doing is to show that we can start from a large scale analysis across different regions, different countries, just using the code, and it's simply it's quite fast and to do it at a short time. And then based on that, it's a way that provide a robust spatial unit for the analysis, because before, as Claudiu said, sometimes the river was just on the boundary and we want to focus in the middle. That's the first thing. And also we want to see what are surrounding it. So using the code, we have the basis to see what is inside of the segments and to have more analysis into the detailed morphology or what other aspects that you're interested in inside this reasonable spatial unit. So for this use case, there are 663 segments, and then it was using the clustering, it was classified into 5 typologies. You can see from here, and this is a way that we generalize into more representative typologies, and based on that, we can do further analysis. For example, the urban climate can be related to the morphologies, and based on that, we can see for each of the type what are the specific interventions you can adapt to. So this is a process that's using Rcrisp to understand the morphology inside the city of the river space.
Yeah, thanks, Yehan. Maybe one thing before handing over to Francesco, one thing to mention here is that this is our let's say first effort or preliminary effort of constructing such a morphotypology. We call this a morphotypology, which can serve all kinds of applications. Yehan mentioned environmental applications, but also other kinds of applications. And that it's limited to Europe simply because we wanted to work with a smaller data set, but it can be done considering the input data, OpenStreetMap, and global digital elevation models. This can be done globally as well. So it's not limited to Europe. So our focus here was on developing the methodology and demonstrating the value of working with such a spatial unit in which the river is central and it's morphologically delineated. But I would like to hand over now to Francesco for the demonstration so that you know how Rcrisp works.
Thanks, Claudiu. Yes, so in this last part of the presentation, I would like to show you how Rcrisp works a bit more in practice, so you can have a bit more feeling of what you can get out of these two concretely. And specifically, I want to show you two things. So the first thing is computational notebooks, where basically you can see how to use Rcrisp in a programming environment. And the second thing that I will show you is a web app where you can instead interact with Rcrisp without having to write any sort of code. So this is the first item that I would like to show you, which is a notebook that illustrates how to use Rcrisp in a programming environment. I will also paste a link to the same notebook in the chat because this is openly available, so you can also scroll through it while I will talk to it. So Rcrisp is a software package written in the R programming language, and as such, it can be used in analysis scripts, or it can be used as a dependency in software in other software packages. The notebook that we are looking at, it's basically code written together with text and the output of the code itself, all bundled together. So these computational notebooks are often used in software engineering to build tutorials and demonstration, but they're becoming more and more used in research as well as a way to demonstrate the use of computational tools, but also as for their reproducibility aspect that they enable due to this capacity of bundling together code and the output that the code generates. And so this notebook shows how to use Rcrisp. And in general, it will show how to use it to delineate urban river spaces. So Claudiu already introduced the concept of delineations. So Rcrisp can delineate urban river areas on the basis of three main spatial units: the river corridor, the corridor segments, and the river space. These are the delineation of these morphological delineations based on infrastructure data, so either the street or rail network or the buildings. There is also this fourth delineation layer, which is actually the starting point of the delineation, which is the river valley, which is used as an initial starting point to guide the delineation of the corridor. In order to draw these delineations, Rcrisp needs some input data, and by default, Rcrisp uses two main sources, which are OpenStreetMap for all the infrastructure data, so street and rail networks, buildings, and other things like the river and geometries and city boundaries. The other data source that we use is Copernicus digital elevation model for the representation of the topographic surface of the area of interest. And we chose it because it's a globally available digital elevation model at a reasonable resolution, so 30 meters. But let me stress the fact that these are just the defaults, but any other data set that provide the same source of information can be used in a combination with Rcrisp as well. Let's now move forward to the more interesting part of the notebook, where we actually carry out the delineation, and you will start to see how text is interleaved by the code that actually run the content of the notebook, and that actually is what produces the output that is visualized here in this document. So I start by importing all the libraries that we use in this notebook. First and foremost, Rcrisp, but also other popular R libraries for geospatial data analysis and visualization. From then, we move on to the main access point of Rcrisp, which is the delineate function. So this is as I said, the main access or entry point to our software package that carries out all the delineation over all the units that we have discussed above. So the corridor, the segments, and the river space. So what we're doing here is to define our study case area, which is defined by a city name and a river name. We chose here Bucharest and Dâmbovița. And we use this we pass these quantities as input to the delineate function that Rcrisp built, which returns the delineations of our area of interest using all the spatial units that we've discussed. So corridor, segments, and the river space. I will show you the result right now. So the first output of the delineation is the geometry of the river corridor. You see here represented on a base map. So this is the area surrounding the river that follows like an initial guess of the valley edge, which are built by the Rcrisp as a starting point, and the corridor is delineated on top of the street and rail network. So you see that the lines follow the OpenStreetMap streets and railway network. The second units the second geometries that Rcrisp produces are the segments. So this is essentially the corridor split by the main transversal streets that cross the Dâmbovița river. These polygons or these geometries can be used, as Claudiu mentioned, for local intercomparison. So to define special units for local analysis, for instance, within a city. The last layer of the delineation is the river space, which is the space included between the river and the first line of buildings. Let me zoom in to have a closer look to how this looks like. You see, this is really the geometry or the area that surrounds the river and which is bounded by the first row of buildings that are facing the river. Now, these units can be used for analysis within an analysis script, can be also exported and used in other software environments or in other contexts. I will show you an example on how this one of these units, especially the corridor, can be used to answer a research question. And in this case, I'm looking at the amount of green space in the surrounding of the river. So I will show you how one can build a cross-scale analysis similar to the one that Yehan or Claudiu described, where one can quantify the percentage of green area in the surrounding of the river. So what we do here is that we define a table of city river pairs that will constitute the cities over which we run the analysis. We then carry out the delineation of the corridors for all these analyses and use this well, we will use this design just next. Let me just show you how these corridors look like on a bigger picture. So those are the 10 cities that we have considered, we are taking from the table above. So zoom into some of these cities, for instance, Rome. This is how the delineated corridor look like. This is Madrid, or Berlin here. You see that without having specified regional specific parameters, we have been able to draw these boundaries in a neutral way, as Claudiu has already described. So we then use these corridor geometries to retrieve information about green areas using as a data source OpenStreetMaps. We show the example for the city of Paris here in a map, where we see the corridor delineated for the city in blue, and the green areas retrieved for the city in green. Once these green areas or this green surface is retrieved for all the cities, we can straightforwardly calculate things like the area or like the surface of these green areas and the surface of the corridor, and estimate the fraction of green area as a percentage, which I then plot as a bar plot here that can help us compare the amount of green spaces in the proximity of the river across these rivers. Here we, for instance, see that the city of Warsaw has the highest a fraction of green area, and Cairo the lowest in the pools. Now, so this is an example of how you can use Rcrisp in this cross-case analysis. When working at Rcrisp, we also realized that not everyone has the skills to write code and to work with Rcrisp in a programming environment. So we also decided to build a web app that would run the most basic functionalities of Rcrisp without having to write any code. So this is also this web app is also publicly available. I will share the link to this later in the chat. And essentially, it provides access to the delineation of corridor and segments with some minimal options. Let me display for our service. So here is Bucharest. Rovica. All right. Finally managed to access the information about the river. And by clicking on the delineate, the delineation process starts. So Rcrisp, which is running under the hood of this web hub, fetch all the required data. So network data, so streets and rail information. Use this to build the internal network. Builds the river valley, runs the delineation of the corridor, and then runs the delineation of the segments. Since this is running, let me also stress the fact that this, so here we got the result. This web app is meant as a demonstration a platform. We are really interested to know if people would want to use it in production. We could think about expanding the capacity because right now the server transit it's quite a limited capacity. So when the output is ready, it can be downloaded, and one can then take the input, the delineated output downloaded, and use it, for instance, as input in your own GIS software. I'm showing here how to import it in QGIS, but simply drag it into the QGIS window. But any QGIS software would be able to open the exported package file. This is all I wanted to show. Claudiu, I give the floor to you.
Thanks, Francesco, for the demo. Just for the last slide, I'm going to take over again. So having explained how it works and demonstrated also the functionality of Rcrisp, we would like to know if you would be interested to be involved in any way. First of all, we are interested in use. This is applicable in other use cases, not only the use cases like the one we showed now, which means they're interested in both qualitative and quantitative analysis that can benefit from using the spatial units created by Rcrisp. So we would like to know how the software could be most useful for you, meaning that the software is in continuous development, and adopting new use cases, we can also adapt the software to the needs of the community. We are interested in contributors who perspectives, so students, researchers, practitioners from different domains, so different levels of usage. If there's anyone software development, we're also very happy to welcome contributions. So Rcrisp is an open source software, which means that it's fully open. Anyone can contribute. If there's anyone about how to work with geospatial data in a programmatic way, maybe they have experience with working in GIS software like QGIS, but not necessarily in a programmatic way, then we're also happy to to have a discussion on that and see how we can use, how we can work together on river space applications. And of course, helping us promoting the software. So if you know anyone who can benefit from this, anyone who has a use case, please feel free to share. There's a lot of information on our open source platform on GitHub, research software directory, and we also share regular information on the Urbanism newsletter. Urbanism is the kind of community practice that we are running within which this software was developed. Yes, and I'm going to end with this, and thank you for your attention. There's more information under these QR codes. Thank you.
Just wanted to thank Claudiu, Francesco, and Yehan for the nice presentation.
Thank you so
Thanks
much.
a lot.
Yeah.
Thank you too for listening, for being here.
Thank you, guys.
Thanks for having us here.